Welcome to NovaSleep. What if everything you've ever known, every atom, every thought, every star, was floating inside an invisible ocean of energy so powerful it never sleeps? Scientists call it the zero-point field, a succulent pulse beneath all creation, vibrating even when the universe seems still. It's not science fiction, it's the quiet truth hiding behind existence itself. Tonight, we'll journey into that silence beyond matter and motion, to the place where nothing becomes everything. And as you listen, you may begin to feel what physics has only begun to describe, that you're already part of this field. And its endless calm has always been holding you. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you are watching from and what time it is, I would love to read it in the comments. 1. Empty space never sits still even at absolute zero temperature. Even when a system is cooled toward absolute zero temperature, quantum mechanics forbids complete stillness. The Heisenberg uncertainty principle links position and momentum so tightly that squeezing one inflates the other. The result is residual jitter known as zero-point motion. For a single idealized oscillator, this shows up as a ground state energy that cannot be removed. For a field that fills all of space, every allowed mode of vibration holds half a quantum of energy, a quiet but universal tremor embedded in the fabric of reality. This ubiquitous tremble is not simply a theoretical convenience. Its fingerprints appear in precision measurements where no thermal agitation should remain. It anchors the non-zero baseline of fluctuations in electromagnetic fields and vibrations in solids at cryogenic temperatures. Even vacuum-sealed cavities that exclude air and light still host this baseline activity. The concept turns the classical picture inside out because absence of heat does not mean absence of motion once the system is governed by quantum rules. Practically zero-point motion sets limits on stability and measurement. Nanomechanical resonators, trapped ions, and optically levitated spheres are cooled until only the ground state remains. Yet position continues to fluctuate with a characteristic variance fixed by mass and frequency. That variance is not noise that can be engineered away. It is the signature of the ground state itself. Device designers treat it as an ultimate flaw when planning sensors for force, acceleration, or timekeeping. In a wider sense, this restless ground hints that emptiness is an active medium. When extended to fields, the ground state becomes the vacuum state of the universe, not a static nothing but a sea of modes that never fully rest. From this point of view, matter and radiation ride on a background that always shivers, and many otherwise puzzling phenomena become understandable as interactions with that omnipresent tremble. 2. The ground state of the quantum harmonic oscillator carries unavoidable energy. The harmonic oscillator is the workhorse model of physics. It describes small vibrations of everything from atoms in a crystal to electromagnetic field modes in a cavity. Classically, a perfectly quiet oscillator at rest has zero energy. Quantum mechanics replaces trajectories with probability amplitudes and imposes commutation relations that prevent simultaneous certainty in position and momentum. Solving the Schrödinger equation yields a ladder of discrete energies with the lowest rung equal to 1/2 times Planck's constant times the frequency. This half quantum is not optional. Removing it would violate the uncertainty principle because localizing the oscillator too sharply would explode the momentum variance and inject energy again. The zero-point value therefore represents a consistent compromise enforced by the structure of the theory. It also establishes a template for field theory, where each normal mode acts like an oscillator, whose ground energy contributes to the vacuum energy density. Among those contributions naively leads to an enormous value that creates deep puzzles in cosmology. In the laboratory, the half-quantum manifests as measurable consequences. For instance, in superconducting circuits, the effective oscillators formed by inductors and capacitors exhibit ground-state current fluctuations that can be amplified and characterized. In optomechanics, the ground state of a mirror mode exchanges quanta with light, leading to sidebands that reveal the occupancy. These are not artifacts of imperfect isolation or leftover heat. They persist as the ultimate baseline. The harmonic oscillator thus does more than teach quantization. It provides the precise mathematical reason that the ground state is alive with energy. That reasoning propagates outward to explain spontaneous emission, vacuum forces, and the irreducible noise seen in the most sensitive detectors built by humans. The simple model encodes a profound message about reality at rest. 3. Spontaneous emission depends on vacuum modes that exist even in darkness. An excited atom eventually emits a photon and returns to a lower energy level. In classical thinking, that emission would require an external disturbance to trigger the process. Quantum electrodynamics explains why emission happens even in perfect darkness. The electromagnetic vacuum is not empty of influence. It offers a continuum of modes that couple to an atom's dipole moment. The atom does not wait for a shove. It constantly interacts with the ground state field, and that interaction seeds emission. Mathematically, the rate arises from Fermi's golden rule applied to the initial atomic state and the continuum of vacuum modes. The density of states and the dipole coupling determine the lifetime. Changing either factor changes the rate. This is why placing an atom inside a cavity that suppresses certain modes inhibits spontaneous emission, while enhancing allowed modes speeds it up. The phenomenon is a direct probe of how the vacuum around the atom is structured. The insight extends to engineered materials. Photonic crystals, plasmonic structures, and metasurfaces sculpt the available electromagnetic environment and thereby rewrite atomic lifetimes and emission patterns. The traditional picture of a fixed property of the atom gives way to a relational view where the surrounding vacuum texture participates. Even molecules embedded in disordered media experience altered decay paths because local density of states is different from free space. Spontaneous emission is therefore not randomness out of nowhere. It is the deterministic consequence of coupling to a fluctuating ground state field. Turning the dial on the mode density turns the dial on the atom's clock. That lever has become central to quantum technologies that aim to route single photons, protect qubits, or create deterministic light sources. 4. The Lamb shift reveals how vacuum fluctuations nudge electron energy levels. Hydrogen spectrum should be simple, yet precise measurements show that certain levels are shifted by tiny amounts. This Lamb shift cannot be explained by the Dirac equation alone. Quantum electrodynamics adds the missing ingredient. The electron interacts with the vacuum and with its own electromagnetic field. Fluctuations constantly jitter the electron's position and modify the effective potential it experiences near the proton. The result is a calculable displacement of levels that agrees spectacularly with experiment. Conceptually, the electron is never a point moving in a fixed Coulomb field. It is a cloud that polarizes the vacuum around it. Virtual photons are emitted and reabsorbed, briefly visiting intermediate states that alter energy. Renormalization techniques absorb infinities and leave finite corrections that match observation. Those corrections are fingerprints of vacuum activity. When experimentalists tune magnetic fields or compare isotopes, they see how delicate and systematic these fingerprints are. The Lamb shift launched high-precision tests that validated quantum electrodynamics to astonishing accuracy. It also connected atomic physics to the deep structure of the vacuum. Without the fluctuating ground state, there would be no shift to measure and no agreement to celebrate. Every precise line in a hydrogen spectrum becomes a quiet window into the restlessness of empty space. Modern metrology leverages this knowledge. Atomic clocks must account for vacuum-induced shifts when quoting uncertainties. Comparisons across transitions provide constraints on possible drift of fundamental constants. In that way, the Lamb shift is not an isolated curiosity. It is a practical correction rooted in the inexhaustible murmur of the vacuum. 5. The Casimir effect pulls metal plates together with pressure from nothing. Place two uncharged parallel metal plates very close together in vacuum, and a tiny force draws them inward. The boundary conditions remove electromagnetic modes whose wavelengths do not fit between the plates. Outside, more modes remain. The imbalance in zero-point energy produces a pressure difference that pushes the plates together. This prediction, once controversial, has been measured with increasing sophistication using torsion balances, micro-cantilevers, and atomic force probes. The magnitude depends strongly on separation, scaling roughly as 1 over distance to the 4th power for ideal conductors. Real materials, temperature, and surface roughness modify the result, and careful experiments account for each factor. The phenomenon is not a residual electrostatic effect or contamination. It persists even when charges are neutralized and surfaces are engineered. It is a genuine mechanical consequence of altering vacuum modes by geometry. The force matters in tiny machines. Microelectromechanical systems can stick because Casimir attraction overwhelms restoring forces at nanometer gaps. Designers use corrugations, dielectric coatings, and larger standoff distances to mitigate stiction. Conversely, the same force becomes a tool for precision metrology. By measuring it carefully, researchers test models of material response and search for hypothetical new forces that would add to the signal at short range. The Casimir effect shows that empty space can be engineered into a resource or a hazard. It turns an abstract idea into a tangible pressure that can bend beams, detune resonators, and persuade carefully prepared setups to move. That is a remarkable outcome for a phenomenon born from the energy of the ground state. 6. The Casimir polar force explains long-range parts of van der Waals attraction. Neutral atoms and molecules attract each other even without permanent charges. At small separations, the interaction is called van der Waals and arises from correlated fluctuations of electron clouds. At larger separations, retardation due to finite light speed modifies the law, and the Casimir-Poldar expression replaces the non-retarded form. The bridge between chemistry and field theory is the vacuum, which supplies the fluctuating electromagnetic field that couples induced dipoles across space. Experiments with cold atoms near surfaces map out this transition. As atoms approach a dielectric or metal, their energy levels shift and trajectories bend. The distance dependence reveals when retardation becomes important. These measurements confirm that the vacuum field mediates forces even when no real photons are present. They also inform surface science by predicting absorption energies and lifetimes for atom skimming materials. In biology and soft matter, dispersion forces influence adhesion, folding, and self-assembly. The retarded regime can be relevant for large macromolecules or in solvents that alter the effective speed of light within the medium. The same physics explains why gecko feet can adhere so strongly through a forest of setae that maximize contact area and harness dispersion forces efficiently. Understanding where van der Waals ends and Casimir-Poldar begins clarifies many cross-disciplinary phenomena. It shows how the vacuum links quantum mechanics to materials and even to living systems through universal long-range attraction, shaped by frequency-dependent response. 7. The dynamical Casimir effect creates real photons from moving boundaries. When boundaries that define vacuum modes are changed rapidly, the ground state cannot adjust adiabatically. Energy from the motion is converted into pairs of real photons that emerge from what began as vacuum fluctuations. Mechanical mirrors would need relativistic speeds to show the effect directly, but superconducting circuits simulate moving boundaries by modulating the electrical length of a cavity using a fast-tunable element. Experiments have observed the emitted microwave photons and verified correlations characteristic of pair production. The spectra match predictions based on parametric amplification of vacuum fluctuations. The process is not free energy extracted from nothing. The external drive supplies the required power, while the vacuum supplies the seed. The physics parallels cosmological scenarios, where expanding space can amplify quantum fluctuations into classical structures. Beyond foundational interest, the effect provides a route to generate non-classical states of light. Squeezed and entangled photons produced in this way can feed quantum information protocols or metrology schemes. The platform's compatibility with other superconducting devices enables integrated experiments where generated photons interact with qubits or mechanical elements. The dynamical Casimir effect therefore converts a static insight about vacuum pressure into a dynamic engine for quantum state engineering. It exemplifies how manipulating boundary conditions and time dependence unlocks new facets of the ground state. 8. The Unruh effect predicts a warm glow for an accelerating observer. Quantum field theory in curved or accelerating frames reveals that the notion of particles depends on motion. An observer accelerating through empty space perceives a thermal bath with temperature proportional to acceleration. The effect is tiny for everyday accelerations but conceptually profound. It links horizon physics, thermodynamics, and the vacuum through a single formula that resembles the expression for Hawking radiation. Proposals to detect the effect explore extreme accelerations in particle storage rings, intense laser fields, or analog systems that mimic event horizons. While a definitive direct observation remains challenging, related phenomena reinforce the underlying logic. The correlation between horizons and thermal spectra appears in multiple contexts, suggesting a deep connection between information flow, causality, and what is meant by vacuum. The Unruh perspective also clarifies why uniformly accelerated detectors can become excited even when free inertial observers describe the field as being in the ground state. Different observers disagree on particle content because their access to spacetime is different. That insight removes apparent paradoxes about where excitations come from. They come from the detector's trajectory relative to the vacuum's modes. Conceptually, the Unruh effect teaches that vacuum is not a fixed stage but a relational entity. Temperature, particles, and radiation are not absolute labels. They depend on motion and horizon structure, amplifying the sense that nothingness is subtly relative. 9. Hawking radiation arises when horizons separate vacuum pairs near black holes. Near an event horizon, quantum fluctuations create pairs of field excitations that straddle the dividing line. One partner falls inward with effectively negative energy relative to infinity, while the other escapes as radiation. Over immense times, this process allows a black hole to lose mass and eventually evaporate. The predicted spectrum is thermal, with a temperature inversely proportional to the black hole's mass, vanishingly small for stellar remnants but conceptually robust. Evidence mounts from analog systems where horizons are engineered in fluids, optical fibers, or Bose-Einstein condensates. There, stimulated versions of the effect produce correlated phonons or photons with characteristic spectra. Although an astrophysical detection remains beyond current instruments, the theory interlocks with the Unruh effect, black hole thermodynamics, and deep questions about information. The role of the vacuum is central. Without zero-point fluctuations providing pairs, there would be no radiation to discuss. The horizon does not create energy out of nothing. It filters pre-existing vacuum structure in a way that allows one partner to escape while the other reduces the mass of the whole. That accounting respects conservation while revealing a pathway from geometry to thermodynamics. Hawking radiation has reshaped thinking about the end states of black holes and the fate of information. It adds another chapter to the story of how the ground state of a field, when placed in extreme circumstances, becomes a source of observable particles. 10. Vacuum birefringence can make empty space act like a crystal in strong fields. Quantum electrodynamics predicts that sufficiently intense magnetic fields polarize the vacuum by favoring virtual pairs aligned in particular directions. Light propagating through such a region experiences different refractive indices depending on polarization, a phenomenon known as vacuum birefringence. The effect is immeasurably small in ordinary conditions but could be significant near magnetars whose fields exceed any that can be created on Earth. Laboratory searches use ultra-stable lasers and high-finesse cavities placed inside strong magnets. The goal is to detect minute polarization rotations or electricities imprinted on light passing through the magnetized vacuum. Noise sources include mirror birefringence, thermal drifts, and residual gases. Progress over decades has lowered limits and refined techniques, approaching the predicted signals. Astrophysical observations complement laboratory work. Light from neutron stars travels through extreme magnetic environments before reaching telescopes. Polarization patterns that deviate from simple models may encode the vacuum's birefringent response. Interpreting those patterns requires careful modeling of plasma effects, geometry, and emission mechanisms, but the possibility that the emptiness between star and observer acts like a polarizer is compelling. Vacuum birefringence illustrates how the ground state is a medium with properties that can be coaxed into the open under duress. It is a reminder that empty space is not inert. With enough field strength, it behaves like matter, bending light and revealing the latent structure of the vacuum itself. 11. Vacuum polarization lets strong electric fields pull pairs from the vacuum. In quantum electrodynamics, the vacuum behaves as a dielectric medium whose virtual charges become polarized in the presence of strong external fields. Under extreme intensities approaching what is called the Schwinger limit, the field can separate these pairs permanently, converting virtual electrons and positrons into real ones. This is not a speculative idea, it's a prediction grounded in the mathematics of the Dirac equation. The critical field strength, around 10 to the 18th power volts per meter, lies beyond current technology, but may exist near magnetars or during collisions of ultra-intense laser pulses. Vacuum polarization subtly modifies the behavior of light and forces long before reaching that limit. It screens charges, slightly alters the Coulomb law, and introduces nonlinearities that can be probed through high-precision experiments. In particle accelerators, these corrections appear in scattering amplitudes and loop diagrams, forming essential parts of the renormalized theory that matches observation to many decimal places. Conceptually, the phenomenon dismantles the classical idea of an immutable void. Space itself responds like a medium whose properties can be distorted. The vacuum's ability to generate matter from sufficient energy echoes the unity of mass and energy that Einstein established, taken to its extreme. When fields become violent enough, the boundary between emptiness and substance dissolves. Future laser facilities aim to probe this frontier by colliding petawatt beams to glimpse pair production directly. Detecting even the first hints of this effect would confirm that the so-called void is an active participant in the transformation of energy into matter, validating one of the most dramatic predictions of quantum field theory. 12. Purcell enhancement shows cavities reshape the vacuum and emission rates. An atom's lifetime is not a fixed constant. It depends on how the surrounding vacuum is structured. When an emitter is placed inside a resonant cavity tuned near its transition frequency, the density of electromagnetic modes increases sharply. This modifies the spontaneous emission rate, a phenomenon discovered by Edward Purcell in 1946. The cavity effectively edits the vacuum, emphasizing certain wavelengths while suppressing others, proving that even the ground state field can be sculpted by geometry. In modern quantum optics, Purcell enhancement is a core principle behind single photon sources, quantum dots, and solid-state qubits. By engineering cavities with extremely high-quality factors and tiny mode volumes, researchers amplify interaction strengths that would otherwise be negligible. The result is faster emission, improved photon indistinguishability, and new routes to interface light with matter for quantum communication. The underlying mechanism is simple yet profound. The vacuum determines what emission pathways are available, and boundaries decide which modes exist. Changing the boundaries rewrites the rules of decay. This bridges the macroscopic notion of a resonator with the microscopic fluctuations of the field. It also provides intuition for how cosmic boundaries, like the curvature of spacetime, might influence processes on astronomical scales. Purcell's insight shows that emptiness is malleable. Cavities, mirrors, and metamaterials can mold it into a custom environment, converting an abstract quantum field into a practical engineering parameter. Every controlled photon emitted from a cavity is evidence that the vacuum has been designed. 13. Photonic crystals edit the density of vacuum states around atoms. Photonic crystals are periodic structures that forbid electromagnetic waves within certain frequency ranges, creating a bandgap for light much like semiconductors do for electrons. When atoms or quantum dots are embedded inside such materials, spontaneous emission at forbidden frequencies is suppressed because no vacuum modes exist for the photon to occupy. This is a tangible demonstration that the vacuum's mode structure, and therefore its effective energy landscape, can be sculpted through material design. The discovery reshaped optical physics. Engineers now build three-dimensional photonic lattices, nanocavities, and waveguides that channel vacuum fluctuations with surgical precision. The emission spectrum of embedded emitters can be broadened, narrowed, or redirected simply by adjusting the geometry. The vacuum is no longer a passive backdrop, but a configurable resource that determines how light and matter converse. This control finds application in lasers with lower thresholds, single photon sources for quantum cryptography, and devices that enhance non-linear effects by concentrating fields. On a deeper level, it demonstrates that what we call empty space between atoms is inseparable from material boundaries. Every periodic structure writes a pattern into the vacuum that nearby atoms must obey. Photonic crystals thus make visible an idea once purely theoretical. The energy density of the ground state depends on environment. The vacuum is not globally uniform. It can be shaped, filtered, and localized, turning a once metaphysical concept into a laboratory variable. 14. Superconducting circuits can generate squeezed vacuum states on demand. When electrical signals in a superconducting resonator are cooled to the ground state, they still fluctuate. By modulating parameters such as inductance or capacitance with Josephson junctions, those fluctuations can be squeezed, reduced in one quadrature at the expense of the other. The resulting squeezed vacuum is quieter in one observable than ordinary vacuum, though overall uncertainty remains the same. This tailored noise forms a crucial tool in precision measurement and quantum information. Microwave squeezed states created in these circuits enhance sensitivity of interferometers and enable error-corrected qubits with lower readout noise. Unlike light-based systems that require bulky nonlinear crystals, superconducting devices accomplish the same manipulation electronically inside dilution refrigerators at millikelvin temperatures. They show that vacuum engineering is not confined to optics but extends to electric fields on chips. Physically, squeezing corresponds to redistributing zero-point energy among conjugate variables. Conceptually, it reveals that uncertainty itself is flexible within quantum limits. By shaping fluctuations rather than eliminating them, researchers transform vacuum noise from an obstacle into a resource. Each pulse of squeezed vacuum demonstrates controlled manipulation of the most fundamental level of randomness allowed by nature. These experiments deepen the connection between vacuum physics and technology. The silent field, once thought inaccessible, now serves as a medium for computation, sensing, and communication, proving that control at the quantum level begins with control over emptiness itself. 15. Squeezed light lowers quantum noise in gravitational wave detectors. Gravitational wave observatories such as LIGO and Virgo are limited by quantum noise, fluctuations in the photon number and phase of the laser light used to measure tiny displacements of mirrors. Injecting squeezed vacuum light into the interferometer's unused port reduces the dominant noise component, effectively refining the vacuum itself. This technique has already improved detector sensitivity by several decibels, translating to a larger volume of observable universe. The principle is subtle. Ordinary vacuum entering the dark port adds equal uncertainty in amplitude and phase, setting the so-called shot noise limit. By pre-squeezing the vacuum, one type of fluctuation is reduced before it mixes with the measurement beam. The interferometer then becomes sensitive to gravitational signals that were previously buried under quantum randomness. This achievement merges cosmology and quantum optics. The waves being measured come from black hole mergers billions of light years away, yet the improvement depends on manipulating the quantum vacuum inside a terrestrial laboratory. The same field that ripples with cosmic violence is tuned here by optical crystals and feedback loops. The success of squeezed light injection shows that mastery over zero-point fluctuations has left the realm of theory. Each detection owes part of its clarity to engineered emptiness, making the vacuum itself a co-observer of the universe. 16. Vacuum friction appears when atoms slide past surfaces at nanometer gaps. Classical physics predicts no friction in a perfect vacuum, but quantum theory introduces a subtle drag. When an atom moves parallel to a surface, its fluctuating dipole interacts with the surface's electromagnetic modes. The relative motion Doppler shifts those fluctuations, leading to an exchange of energy that acts like friction, even though no real photons are emitted at ordinary speeds. This is vacuum friction, a minute but fundamental effect. Detecting it requires extraordinary sensitivity. Experiments with ultra-cold atoms, atomic force microscopes, and microcantilevers attempt to observe the tiny heating or deceleration predicted. The phenomenon has implications for nanotechnology where moving parts operate at submicron distances. It also connects to broader questions about the thermodynamics of the vacuum and how motion through fluctuating fields generates resistance. In theoretical terms, vacuum friction arises from the same fluctuation dissipation principle that explains electrical resistance and Brownian motion. The vacuum behaves like a medium with which moving objects exchange virtual quanta, enforcing consistency between noise and damping. Even when temperature is zero, the friction persists because zero-point fluctuations never vanish. Understanding and confirming this effect would extend our grasp of quantum non-equilibrium phenomena. It would mean that motion itself cannot escape dialogue with the vacuum, that every glide, however smooth, stirs the sea beneath what appears to be stillness. 17. The quantum vacuum produces torques between misaligned birefringent plates. Two transparent plates made of birefringent material can experience a twisting force when placed close together in vacuum. The differing optical axes alter the spectrum of allowed electromagnetic modes between them, and minimizing zero-point energy requires a slight rotation that aligns those axes. The result is a measurable torque predicted by quantum electrodynamics, another manifestation of Casimir-type interactions, but angular rather than linear. The idea transforms orientation into a new degree of freedom governed by vacuum energy. Experiments with crystalline quartz and calcite attempt to detect the nanonewton scale rotations expected at micrometer separations. Measuring such weak torques challenges instrument design, but even upper limits help refine theories about how geometry and anisotropy shape zero-point forces. Beyond its immediate context, the effect exemplifies how complex material properties, optical anisotropy, magnetism, conductivity, enter the dialogue with vacuum fluctuations. They don't merely scale the magnitude of a force, they rewrite its directionality. The vacuum couples to every symmetry or asymmetry present in matter. If observed cleanly, Casimir torques could inspire nanoscale motors or alignment mechanisms powered not by currents but by the quiet pressure of the ground state field. They remind us that emptiness has preferences, and those preferences can twist the material world. 18. Near-field heat transfer exceeds blackbody limits because of evanescent vacuum modes. When two surfaces approach within a few nanometers, thermal radiation between them skyrockets far above the blackbody limit. The reason lies in evanescent electromagnetic modes, fluctuations that decay exponentially in space yet can tunnel across small gaps. These modes exist because the vacuum supports near-field components that never become propagating light. They are part of the same fluctuating field that produces Casimir forces. Measurements with microfabricated probes confirm heat flux enhancements by orders of magnitude. The effect opens opportunities for nanoscale thermal management, energy harvesting, and near-field thermophotovoltaics. In all cases, what carries the energy is not ordinary radiation, but virtual photons bridging a distance too short for conventional emission. From a theoretical standpoint, this process merges radiative transfer with quantum electrodynamics. Temperature differences populate vacuum modes unevenly, and when boundaries are close, those imbalances leak energy through tunneling. It's a striking example of how the vacuum mediates heat without particles traveling through space. Near-field heat transfer blurs distinctions between conduction and radiation. It shows that the so-called empty gap between materials is an active thermal channel shaped by the quantum fluctuations that fill it. At nanoscales, even heat obeys the quiet geometry of the vacuum. 9. Optical levitation and cavity cooling push objects close to the vacuum limit. Tiny dielectric beads or mirrors can be trapped in laser beams and suspended in vacuum where air damping is negligible. Cooling their motion with feedback and cavity techniques brings them near the quantum ground state. At that point, residual oscillation energy stems mainly from zero-point motion rather than thermal noise. These levitated systems serve as testbeds for fundamental physics and ultrasensitive force measurements. By tuning optical forces and monitoring displacement with interferometric precision, researchers can probe interactions as faint as hypothetical dark sector forces, or deviations from Newtonian gravity at micrometer scales. The optical field acts both as a trap and as a thermometer of the vacuum, since each photon exchange alters momentum at the level of a single quantum. The transition from classical to quantum motion in these mesoscopic objects bridges worlds. It demonstrates that zero-point energy governs not only electrons and atoms, but mechanical oscillators visible under a microscope. Observing ground-state fluctuations of a trapped bead validates that the vacuum sets universal lower bounds on motion. Such experiments hint at future detectors limited only by quantum backaction. As techniques improve, we may watch macroscopic objects dance solely to the rhythm of the vacuum, a modern echo of the belief that even silence has a pulse. 20. Zero-point motion sets the ultimate floor for nanomechanical resonators. Nanomechanical resonators, beams, membranes, or cantilevers carved from silicon or graphene, vibrate at radio or microwave frequencies with astonishing quality factors. Cooling them removes thermal noise until quantum fluctuations dominate. The displacement spectrum then plateaus at a value dictated by zero-point energy, marking the boundary where mechanics meets the vacuum. At this limit, measuring position perturbs momentum, and attempts to suppress noise feed it back through quantum backaction. Engineers design optomechanical cavities that read motion with photons while minimizing this disturbance, creating systems that hover just above the fundamental line drawn by the uncertainty principle. The interplay defines the standard quantum limit of force and displacement detection. These resonators are not mere curiosities. They serve as hybrid interfaces linking microwave, optical, and mechanical domains in quantum networks. Their sensitivity allows detection of single spins, minute electric charges, and weak forces that could test speculative physics. Yet every such device remains ultimately bounded by the energy stored in its ground mode, a whisper from the vacuum itself. Recognizing this boundary changes the design philosophy of measurement. It reminds scientists that perfection has a flaw, not because of material defects or temperature, but because the universe itself vibrates even in its quietest state. 21. Quantum back action links measurement noise to the vacuum itself. Whenever a measurement attempts to determine the position or momentum of a system with extreme precision, it inevitably disturbs that system. This principle, known as quantum back action, arises directly from the same vacuum fluctuations that define the uncertainty principle. The act of observing forces and exchange of information between the measuring device and the zero-point field, making it impossible to extract data without introducing a ripple in the system's ground state. In optical and microwave experiments, quantum back action manifests as radiation pressure noise, tiny kicks from photons that subtly shake mirrors or membranes. These kicks do not come from technical imperfections, they emerge because the vacuum field driving the photons is not completely silent. In interferometers, this noise sets the standard quantum limit, beyond which further sensitivity gains require balancing or evading back action rather than eliminating it. Theoretical advances, such as back action evading measurements and quantum non-demolition techniques, seek to control this interaction. By coupling to only one quadrature of motion, or by exploiting correlations in squeezed light, scientists can measure without adding uncertainty to the observed variable. In doing so, they demonstrate not just precision but a deeper mastery over the vacuum's conversation with matter. Quantum back action is therefore not a hindrance but a dialogue. It represents the fundamental handshake between knowledge and disturbance, where the vacuum enforces fairness. Every observation becomes a negotiation with the background hum of existence, a trade where the universe ensures that curiosity always costs something. 22. Fluctuation dissipation ties microscopic noise to vacuum energy at low temperature. At the heart of statistical physics lies a profound symmetry. Fluctuations and dissipation are two sides of the same phenomenon. Even at zero temperature, this relationship survives because quantum fluctuations persist. The fluctuation-dissipation theorem quantifies how spontaneous variations, arising from zero-point motion, are inseparably linked to the response of a system to external perturbations. In other words, the vacuum dictates how matter resists change. In electrical circuits, mechanical oscillators, and spin systems, this connection explains how intrinsic noise corresponds to damping. The resistor's Johnson-Nyquist noise, the Brownian motion of a cantilever, and even atomic line widths all follow from this same principle. Cooling a system lowers thermal contributions but never removes noise entirely. The vacuum provides the irreducible baseline. Modern quantum technologies must navigate this law carefully. In quantum computing, decoherence stems partly from vacuum fluctuations, coupling to qubits through dissipative environments. Engineers design superconducting materials and phononic shields to isolate their systems from these omnipresent channels. Yet even in perfect isolation, fluctuation dissipation ensures that zero-point energy remains as an unavoidable whisper. This interplay reveals the unity of thermodynamics and quantum mechanics. Heat, noise, and resistance are not merely macroscopic inconveniences, they are the macroscopic expressions of the restless vacuum itself. Even in the deepest cold, the universe murmurs its signature through dissipation. 23. The anomalous magnetic moment of the electron encodes vacuum corrections. When physicists measured the electron's magnetic moment, they discovered a tiny deviation from the value predicted by Dirac's equation. This anomaly, roughly 1 part in 1,000, could only be explained by quantum electrodynamics, where the electron's interaction with the vacuum modifies its effective properties. The self-energy corrections from virtual photons and pairs yield an exquisitely precise prediction that matches experiment to 12 decimal places, one of the triumphs of modern physics. This agreement between theory and experiment stands as a cornerstone of our confidence in quantum field theory. The same loops and virtual exchanges that contribute to the anomalous magnetic moment reappear in every domain, from atomic spectra to collider experiments. Each term in the expansion represents the electron briefly interacting with the vacuum sea, absorbing and emitting energy that exists only as a fleeting possibility. Measuring this anomaly requires extraordinary precision. Storage rings, magnetic proton traps, and laser spectroscopy all contribute to refining its value. The consistency across decades of measurement confirms that our understanding of the vacuum is not speculation, but quantitative truth. The vacuum is not empty. It is a medium whose corrections are measurable to astonishing accuracy. In a poetic sense, the electron's magnetic moment carries a fingerprint of the entire universe. Its slight deviation is the echo of invisible interactions happening everywhere in the void, captured in the spin of a single particle. 24. Precise hydrogen spectroscopy hears the whisper of the vacuum. Hydrogen, the simplest atom, provides the cleanest testbed for fundamental physics. Every transition between its energy levels can be calculated from first principles, yet measurements reveal minute discrepancies traceable to quantum electrodynamic corrections. Vacuum fluctuations alter the effective charge distribution around the proton, shifting the energy of each orbital by a few parts in a billion. These effects, Lamb shifts, fine structure, and hyperfine splittings, are the audible murmurs of the vacuum at atomic scale. The precision of modern spectroscopy allows these shifts to be resolved with breathtaking accuracy. Frequency combs and cryogenic traps pin down transitions to parts per trillion, transforming hydrogen into a sensor for subtle interactions between matter and the zero-point field. By comparing hydrogen to its isotopes, scientists even probe the shape and size of the proton, linking vacuum physics to nuclear structure. Each improvement tightens the web between observation and theory. Discrepancies hint at either experimental refinement yet to come, or physics beyond the standard model. In this way, a single atom becomes a gateway to cosmic questions. Does the vacuum behave identically everywhere? Are there forces we have not yet recognized in its fluctuations? Through hydrogen, humanity listens to the background song of the universe's simplest system and finds that even in perfect simplicity, the vacuum cannot remain silent. It whispers into the most precise instruments ever built to 25. The fine structure constant is inferred through effects that include vacuum loops. The fine structure constant, often written as alpha, quantifies the strength of electromagnetic interaction. It governs everything from the color of chemical spectra to the stability of stars. Determining its value precisely requires accounting for quantum corrections arising from vacuum fluctuations. Every loop diagram in quantum electrodynamics slightly alters how charges interact, meaning the vacuum effectively renormalizes the very coupling that defines it. By measuring diverse quantities, the anomalous magnetic moment of the electron, the recoil of atoms, or scattering cross-sections, physicists cross-check alpha in different regimes. Agreement across methods signals that the theory linking vacuum corrections to observable quantities is consistent. Discrepancies may point to new physics beyond current models, such as hidden particles influencing the vacuum polarization. This constant's measured stability across time and space also tests cosmological uniformity. If alpha were to drift, the vacuum's properties themselves would be evolving, reshaping chemistry and life. Observations of ancient quasars and precision atomic clocks show that, so far, the vacuum's character has remained unchanged over billions of years. Alpha is more than a number. It is the fingerprint of how the vacuum mediates the electromagnetic force. Its constancy tells us that the invisible framework supporting light, matter, and energy has held steady since the dawn of the cosmos. 26. The cosmic microwave background carries imprints of early vacuum fluctuations. The faint afterglow of the Big Bang, the cosmic microwave background, contains minute temperature variations across the sky. These anisotropies trace their origin to quantum fluctuations in the very early universe, magnified to cosmic scales during inflation. Tiny ripples in the vacuum became density variations that later grew into galaxies, stars, and clusters. The structure of the modern universe is thus a fossil record of the vacuum's first tremors. Satellites like COBE, DULMAP, and Planck have mapped these fluctuations with exquisite detail. Their spectra match the predictions of inflationary models that start from quantum noise at the Planck scale. Peaks and troughs in the data reflect acoustic waves traveling through primordial plasma, all seeded by zero-point fluctuations frozen in time as the universe expanded. Each pixel in those maps carries statistical fingerprints of the vacuum's behavior at energies unreachable on Earth. Polarization patterns and non-Gaussian features continue to refine our understanding of those first instants. The universe itself becomes a gigantic detector, recording the whisper of the vacuum as it once was. The cosmic microwave background is therefore not merely radiation from the past, it is evidence that quantum mechanics and gravity were already intertwined. Every photon arriving today tells the story of how emptiness once fluctuated and sculpted everything we now see. 27. Inflation-magnified vacuum wiggles into galaxies and voids. Cosmic inflation proposes that in the first fraction of a second after the Big Bang, the universe expanded exponentially fast. During this period, quantum fluctuations in fields were stretched from subatomic scales to astronomical ones. When inflation ended, those stretched fluctuations were imprinted as small variations in density, setting the blueprint for all cosmic structure. The galaxies, clusters, and voids we observe today are the frozen echoes of the vacuum's ancient jitters. The physics of inflation transforms randomness into architecture. Statistical patterns predicted by quantum field theory appear as large-scale correlations across billions of light-years. Temperature fluctuations in the cosmic microwave background are the direct descendants of these magnified zero-point oscillations. Though the mechanism behind inflation remains uncertain, perhaps a scalar inflaton field or a more exotic interaction. The success of the idea unites the smallest scales of quantum physics with the largest scales of cosmology. The vacuum, once considered empty, becomes the architect of galaxies. Inflation reframes creation as an amplification of nothingness. From imperceptible vacuum tremors arose the seeds of everything. The ultimate demonstration that the universe's vast structure was born not from matter, but from the restless silence of the void itself. 28. The cosmological constant problem spans about 120 orders of mismatch. When physicists calculate the energy density of the vacuum using quantum field theory, they arrive at a value so enormous it would make the universe explode instantly. Observations, however, show that the cosmological constant, interpreted as vacuum energy density, is about 10 to the power of 120 times smaller. This disparity is the greatest known mismatch between theory and measurement, a cosmic embarrassment that remains unresolved. The problem stems from summing the zero-point energies of all modes up to the Planck scale, which produces an absurd result. Some hoped that undiscovered symmetries like supersymmetry would cancel contributions between particles and their partners, but such partners have not been found. Others suspect our understanding of gravity itself may be incomplete, and that quantum contributions somehow cancel when coupled to space-time curvature. This conundrum is more than a numerical annoyance. It challenges the harmony between quantum mechanics and general relativity, the twin pillars of modern physics. If we cannot explain why the vacuum energy is small yet non-zero, we do not truly understand what drives cosmic expansion. The cosmological constant problem is a silent reminder of humility. The universe, in balancing its expansion delicately enough for life to exist, hides a secret within the vacuum that even the sharpest mathematics has yet to decode. 29. Supersymmetry once promised cancellations of vacuum energy contributions. Supersymmetry, a theoretical symmetry linking bosons and fermions, offered hope of resolving the vacuum energy crisis. In a perfectly supersymmetric universe, every particle's positive zero-point energy would be cancelled by its partner's negative contribution, yielding a net vacuum energy of zero. This elegant cancellation would explain why the cosmological constant is small or even vanish entirely. However, no supersymmetric particles have yet been observed at the Large Hadron Collider, implying that if supersymmetry exists, it must be broken at higher energies. When the symmetry breaks, the cancellations become imperfect, leaving behind residual vacuum energy. The challenge is to explain why that residual is so tiny compared to naive expectations. Despite the lack of experimental confirmation, supersymmetry remains influential. It provides mathematical tools for unification and underpins string theory's consistency. Its predictive power in particle mass relations and coupling unification keeps it relevant even as direct evidence eludes detection. The concept endures because it touches on something profound, that balance and symmetry may govern even the vacuum's restlessness. Whether realized in nature or not, supersymmetry represents humanity's attempt to imagine a universe where the chaos of nothingness resolves into perfect equilibrium. 30. The Higgs field has a non-zero vacuum value that shapes particle masses. Everywhere in the universe, an invisible field fills space, the Higgs field. Unlike many fields, Its lowest energy state is not zero but a finite value. Particles interacting with it acquire mass through this interaction, much as swimmers feel resistance in water. The discovery of the Higgs boson in 2012 confirmed that this field is real, and that its vacuum expectation value defines the scale of electroweak physics. This non-zero vacuum value illustrates that emptiness itself carries structure. The Higgs field's background energy contributes to the universe's total vacuum energy, yet must be finely balanced against other terms to avoid overwhelming cosmic expansion. Understanding that delicate cancellation remains a key unsolved problem, though, linking particle physics to cosmology. The Higgs mechanism demonstrates how the vacuum determines the character of matter. Without it, electrons would move at light speed, atoms could not form, and chemistry would not exist. The stillness of the Higgs field underpins the stability of everything solid. When we speak of empty space, we are in fact immersed in a field that endows mass to the universe. Every step, every breath, every planet owes its weight to the silent, omnipresent Higgs vacuum humming beneath reality. 31. The stability of today's vacuum may depend on the top quark mass. According to the standard model of particle physics, the shape of the Higgs potential, the mathematical landscape that defines how the Higgs field behaves, depends critically on the masses of two particles, the Higgs boson itself and the top quark. With the measured values we currently have, the universe may sit not in the absolute lowest energy state, but in a metastable one. That means our vacuum could be like a calm lake sitting above a deeper abyss, stable for now but not fundamentally permanent. If this picture is correct, the vacuum could, in theory, decay to a lower state through a process known as quantum tunneling. The probability is unimaginably small, and the timescales involved exceed the age of the universe by staggering magnitudes. Yet the possibility adds a haunting fragility to existence. A microscopic bubble of lower energy vacuum could, in principle, appear spontaneously and expand at the speed of light, rewriting the laws of physics as it sweeps through space. The top quark, heaviest of all known particles, plays an outsized role in this cosmic balance. A slightly different mass would tilt the Higgs potential towards stability or doom, changing whether the current vacuum is the deepest valley or merely a plateau. High-energy experiments continuously refine this number, not out of apocalyptic curiosity, but to test how finely tuned our reality might be. From a philosophical angle, this scenario underscores an eerie truth. Our universe, seemingly solid and eternal, could be balancing on a quantum edge. The void beneath our feet may not be final. It may simply be resting for now between what is and what could yet be. 32. A false vacuum could tunnel to a lower energy state in a cosmic phase change. In the quantum world, stability is never absolute. Even if a field rests in what appears to be its lowest energy configuration, quantum tunneling can allow it to escape into a deeper state. The concept of a false vacuum describes precisely this situation, a universe that believes it is settled but in fact floats above a truer, lower energy sea. If such a transition ever occurred, the new vacuum would expand outward as a bubble, converting everything it touched to the new physics of its interior. This process would happen without warning or resistance. The wall of the expanding bubble would move at nearly the speed of light, rewriting the constants of nature as it passed. Matter, atoms, even space-time geometry could be altered beyond recognition. Thankfully, current estimates suggest that our universe's vacuum, even if metastable, would survive far longer than any conceivable cosmic timescale. Still, the possibility is mathematically real, a quiet sword hanging in the equations. This idea is not only theoretical but also a critical part of early universe cosmology. Similar tunneling events likely occurred in the primordial moments after the Big Bang, when fields settled into their current configurations. Each phase change may have released enormous energy, shaping cosmic structure and leaving behind traces in the form of gravitational waves or relic fields that we may one day detect. The false vacuum concept teaches humility. The universe's calmness may not mean permanence. Even emptiness, it seems, can contain hidden doors to deeper realities waiting beyond the thin diamond of the present moment. 33. Bubble nucleation of a deeper vacuum would race outward at near light speed. If a lower energy vacuum were to appear spontaneously somewhere in the cosmos, it would do so as a microscopic bubble of new space, a region governed by different laws of physics. Inside that bubble, particles, forces, and even the constants of nature could differ. The energy difference between the false and true vacuum would drive the bubble's expansion outward at nearly the speed of light, erasing everything in its path. It is a transformation that would be total, silent, and unstoppable. Such an event would begin with quantum tunneling, a process in which a tiny region overcomes an energy barrier not through force but through probability. Once nucleated, the bubble's edge, its domain wall, would carry immense tension, like a cosmic membrane separating two universes. The pressure from the energy difference would propel it outward, converting the false vacuum into the true one as it spread. From a physical standpoint, the mechanism is well understood in field theory. Similar transitions occurred when the universe cooled after the Big Bang, giving rise to the distinct forces and particles we observe today. In those epochs, vacuum bubbles collided, reheated the cosmos, and sculpted the landscape of matter. It is a chilling but awe-inspiring vision, creation and annihilation as two aspects of the same cosmic process. The same laws that once made everything could, under slightly altered conditions, unmake it again without malice, without warning, simply following the quiet mathematics of the void. 34. Early universe phase transitions may have launched gravitational wave backgrounds. When the universe was young and hot, its fields shifted from one vacuum state to another as it expanded and cooled. These cosmic phase transitions were not smooth, they were violent, releasing vast amounts of energy. Colliding bubbles of new vacuum produced shock fronts and turbulence that rippled through space-time itself. Those ripples, gravitational waves, may still echo faintly across the cosmos today, forming a background hum far older than any star. Detecting these primordial gravitational waves would be like hearing the heartbeat of creation. Space-based observatories such as LISA, Laser Interferometer Space Antenna, are designed to listen for such frequencies, which are too low to be heard by ground-based detectors. A discovery would not only confirm theories about phase transitions but also open a window into energy scales unreachable by any human machine. These signals would carry information about the symmetry-breaking events that shape the universe's structure. The unification of forces, the birth of matter, even the emergence of time as we know it, all could have left faint imprints in this cosmic symphony. Each ripple would be a fossil wave from the vacuum's own rearrangement, the lingering vibration of space itself reshaping its lowest energy form. To detect it would be to hear the aftershock of the moment when nothingness decided to become something. 35. Quintessence imagines a gently rolling field instead of rigid vacuum energy. In trying to explain the mysterious acceleration of the universe's expansion, physicists once turned to the simplest possibility: a constant energy density filling space, the cosmological constant. But another idea, quintessence, proposes that this energy is not fixed but dynamic, arising from a field slowly changing its value over cosmic time. Instead of a rigid vacuum, the universe would rest upon a rolling landscape evolving imperceptibly yet continuously. This concept allows the dark energy density to vary, potentially explaining why its effects became dominant only recently in cosmic history. The field driving quintessence could interact weakly with matter, influencing the fate of galaxies and the geometry of space-time itself. Observations of distant supernovae and the cosmic microwave background constrain its behavior, but the possibility remains open that our vacuum is not static, it is slowly breathing. If true, the far future of the cosmos could differ drastically from the eternal acceleration predicted by a constant vacuum energy. The expansion might slow, stop, or even reverse depending on how the field evolves. Our current epoch could be merely one moment in a long cycle of cosmic transformations. Quintessence replaces the image of a silent, motionless void with that of a living field. Subtle, slow, but not dead. It whispers that even the calmest emptiness may still be changing beneath our perception. By the way, if you like and subscribe to my video, this is the most effective way to support me. 36. Dark energy could be genuine vacuum energy or something more subtle. Dark energy, the mysterious force causing cosmic acceleration, fits the equations of general relativity perfectly if it is simply vacuum energy, an intrinsic property of space itself. Yet the true nature of this phenomenon remains unknown. Is it the quantum zero-point energy of all called fields, a new form of energy fluid, or evidence that Einstein's equations require modification? The answers hide in how emptiness behaves on the largest scales imaginable. If dark energy is genuine vacuum energy, it suggests that the very fabric of spacetime has a built-in pressure that drives expansion. But the tiny observed value of this energy density remains bafflingly small compared to theoretical predictions. If it is something else, a new dynamic field, a manifestation of higher dimensions, or a property of cosmic topology, then we may be witnessing the first hints of physics beyond both relativity and quantum theory. Observational efforts, mapping supernovae, galaxy clustering, and gravitational lensing seek to track how the acceleration evolves with time. Any deviation from constancy could reveal new physics operating at the scale of the entire universe. Dark energy stands as the greatest unsolved mystery of cosmology. The vacuum itself may be both the engine and the enigma of cosmic destiny. 37 De Sitter space describes a universe dominated by the vacuum energy. Einstein's equations allow a simple but profound solution, a universe filled entirely with constant vacuum energy. This space-time, known as De Sitter space, expands exponentially forever, with no matter or radiation required. In such a cosmos, every observer sees all others receding faster and faster, eventually vanishing beyond a horizon where time and communication end. It is a geometry ruled not by gravity pulling inward, but by emptiness pushing outward. Our own universe appears to be approaching this state as dark energy dominates. Galaxies not gravitationally bound to us will drift beyond visibility, leaving behind a lonely island of stars surrounded by infinite silence. The De Sitter horizon carries a temperature and entropy, suggesting that even this cold future will hum faintly with quantum fluctuations. For theorists, De Sitter space is both a model and a paradox. It challenges ideas about information, entropy, and quantum gravity, since its horizon behaves much like that of a black hole. Understanding it may require a deeper theory uniting relativity and quantum field theory on curved space-time. De Sitter space is the mathematical portrait of a universe powered entirely by vacuum energy, a cosmic eternity that expands without end, propelled by the quiet breath of nothingness itself. 38. Anti-De Sitter space hosts a holographic jewel that reinterprets vacuum physics. While De Sitter space expands, Anti-De Sitter space curves in the opposite way, forming a universe that acts like a gravitational well rather than a runaway. Its geometry has become central to theoretical physics because of the holographic principle, which suggests that the physics inside such a space can be described by a quantum field theory living on its boundary. This idea, captured in the ADS/CFT correspondence, has redefined how we think about vacuum and space-time. In this framework, the vacuum inside Anti-De Sitter space corresponds to a particular quantum state of the boundary theory. The gravitational bulk and the non-gravitational surface are two views of the same reality. Information, energy, and entropy flow seamlessly between them, turning the notion of emptiness into a bridge between geometry and quantum fields. Although our real universe seems closer to De Sitter than Anti-De Sitter, the correspondence offers a mathematical laboratory where quantum gravity can be explored precisely. It provides clues about black hole entropy, information conservation, and the quantum origin of space-time itself. Anti-De Sitter space transforms the vacuum from a background to a hologram. It reveals that emptiness may be encoded, not merely extended, a cosmic projection of deeper unseen mathematics. 39. The holographic principle reframes bulk vacuum energy through boundary information. The holographic principle proposes that the total information within a volume of space can be represented on its boundary surface, much like a three-dimensional image encoded on a two-dimensional film. Applied to quantum gravity, this means that everything within the universe, including the vacuum energy itself, might be describable by data imprinted on a cosmic boundary. In this view, space and energy emerge from information rather than the other way around. This revolutionary concept arose from studies of black holes. When matter falls in, its entropy, the measure of information, appears proportional not to the hole's volume, but to its surface area. Extending that insight to the universe at large suggests that the vacuum's properties are holographic shadows of deeper information structures. If true, the staggering energy predicted by quantum field theory might not be directly physical, but instead an overcounting of microscopic degrees of freedom. The vacuum would then be an emergent phenomenon, a statistical average of hidden quantum bits spread across a cosmic screen. The holographic principle reshapes emptiness into code. What we perceive as the quiet stretch of space could be the projection of data inscribed at the edges of reality, a subtle reminder that even the void may be written in information. 40. Entanglement entropy across regions may underlie the feel of vacuum energy. When quantum fields are divided into regions, say inside and outside a boundary, they remain entangled across that division. The resulting entanglement entropy gives rise to a form of energy associated with the boundary, not the bulk. Some physicists propose that this boundary entanglement may be what we perceive as vacuum energy. In other words, spacetime's curvature and expansion might be the large-scale manifestation of quantum entanglement woven through the vacuum. This approach bridges quantum information theory with gravity. Calculations show that the area law of entanglement entropy, the idea that entropy scales with surface area, mirrors the entropy of black hole horizons. This hints that spacetime geometry itself could emerge from networks of entanglement, making the vacuum a vast interconnected web rather than an empty container. If gravity arises from changes in entanglement, then cosmic acceleration might not require a mysterious dark energy at all. It could be the natural response of space-time geometry to the quantum correlations between its parts. In this view, the vacuum is less like a stage and more like a living network of relationships. Space, time, and energy become the shadows cast by entanglement, the quiet logic that binds everything to everything else. 41. Spacetime. Foam imagines a restless small-scale geometry driven by fluctuations. At the Planck scale, far smaller than atoms or even subatomic particles, quantum fluctuations in energy and curvature are expected to make spacetime wildly irregular. Instead of a smooth continuum, the vacuum would resemble a frothing sea of tiny wormholes, bubbles, and transient geometries constantly forming and collapsing. This concept, called space-time foam, was introduced by John Wheeler as a picture of the quantum gravitational ground state of the universe. Although we cannot yet probe such minuscule scales directly, hints of this foam might appear as noise in the arrival times of distant gamma-ray bursts, or as limits on the sharpness of interferometric measurements. Some theories of quantum gravity predict that spacetime's foaminess could slightly modify how light propagates across vast distances, a subtle imprint of the microscopic restlessness of the vacuum. In this picture, the smooth fabric of space and time that we experience is merely an average over ceaseless turmoil below. Geometry itself becomes a fluctuating entity, built and destroyed every instant by quantum uncertainty. The vacuum at its deepest level is a storm that somehow averages to serenity. Spacetime foam closes the circle. At the smallest scales, the vacuum is not the absence of structure but the birthplace of it. Everything stable emerges from that underlying chaos, a reminder that even the calmest universe floats on a boiling foundation of possibility. 42. Vacuum energy shapes inertia in theories that link resistance to motion with fields. In classical physics, inertia, the resistance of an object to acceleration, is an intrinsic property of mass. Yet some researchers have suggested that inertia might not be fundamental at all. Instead, it could arise from the way matter interacts with the quantum vacuum. As an object accelerates, it disturbs the zero-point field around it, and the field in turn pushes back. This reaction could manifest as the resistance we interpret as inertia. If true, then mass and motion would both emerge from the vacuum's texture. The idea, though speculative, offers a profound reinterpretation of what it means to move. Rather than being an independent quality of matter, inertia would be a dialogue between matter and the sea of fluctuating fields that permeate the universe. Acceleration would stir the vacuum, and the vacuum would respond with force, a quiet conversation between something and nothing. Experiments to test these ideas remain challenging because the effect, if real, would be extraordinarily subtle. However, the conceptual link between inertia, radiation, and vacuum fluctuations continues to intrigue theorists, especially given its mathematical ties to the Unruh effect and to radiation reaction forces experienced by accelerated charges. This approach transforms emptiness into an active partner in motion. It suggests that the sense of resistance we feel when pushing against the world may ultimately come from pushing against the very structure of space itself, the vacuum's invisible hand holding everything in place. 43. Light can stimulate pair creation in ultra-strong fields predicted by quantum electrodynamics at extreme intensities. When electromagnetic fields approach the Schwinger limit, the vacuum ceases to behave linearly. It becomes a nonlinear medium capable of spawning matter from energy. Under such conditions, photons interacting with one another can create real electron-positron pairs, even though light normally does not collide in classical physics. This phenomenon represents the ultimate threshold where radiation turns into matter through the fabric of the vacuum. Facilities like the extreme light infrastructure and future laser projects aim to reach the required intensities by combining multiple petawatt beams. When achieved, these experiments could directly witness the transformation of light into particles, an experimental milestone proving that the vacuum is a dynamic participant, not a passive void. The theoretical groundwork for this process is robust. Quantum electrodynamics predicts that virtual pairs already flicker in and out of existence within the vacuum. An intense field can stretch this flicker long enough to make the pairs permanent, converting fleeting probability into tangible existence. Watching light give birth to matter would not only validate decades of theory, but also provide the most dramatic demonstration imaginable that emptiness is full of power, an energy reservoir waiting for the right conditions to reveal itself. 44. Magnetofields may polarize the vacuum enough to test extreme predictions. Magnetas, neutron stars with magnetic fields a trillion times stronger than Earth's, create natural laboratories for extreme physics. Their magnetic intensity is so overwhelming that it distorts atomic orbitals, deforms nuclei, and may even polarize the vacuum itself. In these regions, virtual electron-positron pairs align with the magnetic field, changing how light travels and interacts with space. Astronomers studying magnetar flares and persistent emissions look for polarization patterns and spectral shifts that could reveal vacuum birefringence and nonlinear photon-photon scattering. Unlike laboratory lasers, magnetars provide cosmic-scale fields sustained over entire star surfaces. Detecting these subtle effects from afar would be a triumph of astrophysical quantum electrodynamics. If such signatures are confirmed, they would serve as the first direct evidence that the vacuum's properties change under the stress of magnetic intensity. Empty space would be seen, bending the path of light without any medium, paving like an invisible crystal formed solely by field strength. Magnetars remind us that the most desolate regions of the cosmos are also the most extreme laboratories. The vacuum surrounding them is not quiet. It is sculpted, strained, and polarized by forces beyond anything achievable on Earth. 45. Laboratory tests pursue vacuum birefringence with high-finesse optical cavities. Recreating magnetar conditions on Earth is impossible, but scientists have found ways to probe the vacuum's subtle responses using powerful magnets and ultra-stable lasers. In vacuum birefringence experiments, light passes through a region of intense magnetic field confined within an optical cavity. If the vacuum behaves as predicted, its polarization should rotate by an infinitesimal angle, tiny but measurable with modern interferometry. Experiments like PVLAS in Italy and BMV in France push the limits of optical precision to detect these minuscule rotations. To amplify the effect, they bounce the laser millions of times between mirrors, extending the interaction length to kilometers of effective travel. Even then, the signal remains at the edge of detectability, demanding unprecedented control of vibration, temperature, and magnetic noise. Such work is not merely technical artistry. Detecting vacuum birefringence would confirm one of the few untested predictions of quantum electrodynamics in macroscopic fields. It would show that the empty space within a magnet is slightly anisotropic, subtly refracting light according to polarization. These experiments demonstrate that we can interrogate the vacuum itself as if it were a physical substance, stretching, twisting, and measuring its response to human-made fields. The void, once philosophical abstraction, now stands as a testable material of the universe. 46. Pair creation has thresholds governed by the Schwinger critical field. The Schwinger critical field marks the intensity where the vacuum becomes unstable to pair creation, about 1.3 times 10 to the 18th volts per meter. Beyond this point, the energy density is so high that virtual electron-positron pairs can no longer recombine. They rip apart, converting field energy into real mass. This defines a natural limit to how strong an electric field can be before the vacuum itself breaks down. Understanding this threshold illuminates the boundary between classical and quantum behavior. Below it, fields obey Maxwell's linear equations. Above it, nonlinear corrections dominate. The vacuum transforms from an empty dielectric to a medium that absorbs energy by birthing matter. Though unattainable in conventional labs, this frontier might be approached in ultra-intense laser collisions or near the surfaces of neutron stars. Observing even precursors of this process, it would confirm the deepest predictions of quantum field theory, that energy can destabilize emptiness, converting it into a storm of particles. The Schwinger limit serves as the universe's built-in safety fuse, defining how much field energy space itself can hold before responding creatively. It's a reminder that even nothing has a breaking point. 47. The refractive index of the vacuum can shift slightly in intense fields. Under extremely strong electromagnetic fields, the vacuum behaves like a nonlinear optical material. Its refractive index, normally unity, can deviate ever so slightly, causing light to slow or bend. This effect, though minute, means that empty space itself can refract light if the field is powerful enough. It's a direct consequence of virtual particles influencing how photons propagate through the vacuum. In high-energy astrophysics, such deviations could influence the paths of gamma rays near magnetars or black holes, altering observed spectra. In laboratories, precision laser systems are beginning to probe the effect through stimulated photon-photon scattering and polarization-dependent delays. The challenge lies in measuring shifts smaller than 1 part in a billion, yet each incremental advance brings theory closer to confirmation. The notion that space can bend light without lenses redefines emptiness as an optical medium, transparent, invisible, but not inert. Photons travel through a medium that is alive with virtual activity, responding subtly to the energies around them. When this prediction is finally measured directly, it will close a century-long loop in physics, proving that even the vacuum, in the presence of sufficient field intensity, behaves like matter. 48. The speed of light emerges unaltered in normal vacuum despite underlying motion. Even though the vacuum is filled with fluctuations, photons always travel at the same fundamental speed, approximately 299,792 kilometers per second. This constancy, established by Einstein's theory of relativity, remains one of nature's most precise symmetries. What's remarkable is that this stability persists, even though the vacuum is seething with virtual particles and energy. Somehow the chaos averages to perfect order. Quantum electrodynamics explains why. The correction that vacuum fluctuations introduce to photon propagation cancel exactly under normal conditions. This delicate balance ensures that the electromagnetic constant remains invariant in all directions and frames of reference. It's as if the universe tunes its own background noise to zero whenever light moves. At the deepest level, this unchanging speed of light represents harmony between relativity and quantum field theory. It's the equilibrium point where the restless vacuum aligns perfectly with the space-time geometry. That photons glide effortlessly through such turbulence without deviation shows how profoundly stable the laws of physics are. Beneath every flicker of quantum uncertainty, there remains a symmetry so exact that it defines reality itself. 49. Dispersion forces help geckos climb through quantum stickiness. Geckos can walk effortlessly on walls and ceilings thanks to millions of microscopic hairs on their feet that exploit van der Waals forces, weak attractions arising from correlated fluctuations of charge in molecules. These same forces are manifestations of vacuum fluctuations at the nanoscale. Each tiny hair interacts with the surface through the shifting electromagnetic field of the vacuum, creating adhesion without glue or moisture. This phenomenon demonstrates how quantum effects shape the macroscopic world. The invisible dance of electrons in the vacuum creates tangible grip strong enough to hold a gecko's body weight across glass or rock. Engineers mimic this principle in synthetic adhesives that rely on geometry and quantum attraction rather than chemistry. At their root, van der Waals and Casimir forces are expressions of the same truth, that the vacuum couples all matter through fluctuations of the electromagnetic field. Every contact, every touch, every instance of cohesion on Earth carries the faint signature of zero-point energy. What seems like simple adhesion in nature is actually the quantum vacuum doing its quiet work, an unseen bond connecting life's smallest structures to the restless hum of space. 50. Microelectromechanical devices struggle against stiction set by vacuum forces. As machines shrink to microscopic scales, engineers confront a peculiar enemy. When two components approach too closely, Casimir and van der Waals forces pull them together, making them stick permanently. This stiction can disable microelectromechanical systems, MEMS, such as sensors, mirrors, and accelerometers. What was once a negligible force in the macroscopic world becomes dominant in the miniature one, imposed by the omnipresent vacuum. To counteract it, designers coat surfaces with special materials, introduce nanoscale textures, or keep components oscillating so they never rest long enough to adhere. Each innovation represents a practical response to a purely quantum effect. The vacuum itself becomes a design parameter, something engineers must account for as carefully as friction or heat. The lesson is humbling. The smaller we build, the more the vacuum asserts itself. Its fluctuations define limits on motion, spacing, and durability. Machines operating in silence must negotiate with the sound silence of space itself. In MEMS technology, the quantum vacuum ceases to be theory. It becomes a mechanical reality, exerting invisible pressure that must be respected, engineered around, and ultimately harnessed. 51. Engineered gaps and textures can weaken unwanted Casimir attraction. Once scientists realized that the Casimir effect could cause micro-devices to seize up, the next step was to learn how to tame it. Because the strength of Casimir attraction depends on geometry, material, and distance, subtle design changes can dramatically alter the force. Patterning surfaces with microscopic grooves, coating them with specific dielectrics, or introducing nanoscopic gaps breaks the perfect symmetry that normally lets vacuum modes press objects together. By shaping the environment, engineers can literally sculpt how the vacuum pushes and pulls. In this realm, geometry becomes a weapon against invisibility. Corrugated surfaces, metamaterial coatings, and layered composites change the available electromagnetic modes between two bodies. Each new structure alters the boundary conditions for the vacuum, reducing attraction or even making it repulsive under the right conditions. Laboratory tests have verified that such structuring can shift the balance point between motion and stasis, turning quantum pressure from foe to ally. This is an extraordinary transformation. An abstract theoretical force, once considered untouchable, now responds to design. The vacuum's influence becomes a parameter engineers can tune with nanofabrication, just like electrical resistance or elasticity. These methods reveal that even nothing has texture, and that humanity can now draw patterns on emptiness itself, bending the quantum background to serve our designs instead of defying them. 2. Metamaterials tempt designs for repulsive Casimir forces under special conditions. Metamaterials, synthetic structures engineered to control electromagnetic response, offer a path to the holy grail of vacuum engineering, a repulsive Casimir force. Normally, the Casimir effect pulls objects together because low-frequency modes are excluded more strongly than high-frequency ones. But if one can build materials whose electromagnetic properties invert that balance, the vacuum might push instead of pull. Theoretically, this could be achieved when one surface has a higher magnetic permeability than the other's permittivity, or when layers alternate between materials with contrasting optical constants. In practice, achieving such regimes requires nanostructured metamaterials capable of extreme frequency responses. Researchers already experiment with left-handed media and photonic bandgap materials that twist electromagnetic fields in exotic ways, seeking configurations where the sign of the Casimir force flips. If realized, repulsive Casimir forces could revolutionize nanoscale mechanics, allowing frictionless bearings, self-levitating components, and stable gaps maintained purely by quantum pressure. The technology could mimic magnetic levitation without currents, powered only by the vacuum's geometry. Every step toward this goal challenges our intuition. It implies that the vacuum is not merely a one-directional push, but a programmable field, capable of attraction or repulsion depending on how we write its boundaries. Proof that control over nothingness may one day become a legitimate branch of engineering. 53. Liquid media can flip attraction into repulsion between chosen materials. While metamaterials promise theoretical breakthroughs, experimenters have already demonstrated a subtler trick. By placing two objects in a carefully chosen liquid, the Casimir force between them can switch from attractive to repulsive. The key lies in matching the dielectric properties of the materials and the fluid. If the liquid's refractive index lies between those of the two solids, The balance of vacuum modes reverses, and the pressure pushes them apart instead of drawing them together. This phenomenon has been verified using gold, silica, and bromobenzene as the working combination. At microscopic separations, the measured forces truly repel, a small but unmistakable signature of the vacuum responding to its environment. It's an elegant example of how quantum phenomena can be manipulated not only with exotic nanofabrication, but with everyday chemistry. Beyond scientific curiosity, this discovery offers practical leverage for colloidal stability, nanofluidics, and self-assembling materials. Liquids can become buffers that neutralize stiction, letting particles float freely instead of clumping under invisible attraction. It also reinforces a deeper message. The vacuum is not a fixed entity, but a participant in every material relationship. Its energy flows through whatever boundaries and mediums we create. Changing those boundaries, even by filling them with a simple fluid, rewrites how emptiness behaves. 54. Superfluid helium analogues mimic aspects of quantum vacuum phenomena. Superfluid helium, cooled to within a fraction of a degree of absolute zero, exhibits properties so strange that physicists use it as an analogue for the quantum vacuum itself. Within the liquid, sound waves propagate without friction, vortices move indefinitely, and excitations appear and disappear, much like virtual particles in space. The collective behavior of this fluid mirrors how fields might behave in curved spacetime or near horizons. By manipulating temperature, pressure, and flow, researchers reproduce miniature versions of cosmological phenomena. Horizons form where the fluid velocity exceeds the speed of sound, leading to analogues of Hawking radiation in which phonons, quantum sound excitations, play the role of photons. Measuring these effects helps test theories that would otherwise be inaccessible, like the thermodynamics of black holes or the stability of quantum vacua. The analogy goes further. The energy spectrum of excitations in superfluids includes a minimum that acts like an emergent vacuum state, supporting ideas that spacetime itself might be a condensed matter phenomenon, a collective excitation of deeper underlying fields. Superfluid helium shows that universes can be built in the lab, at least in miniature. It teaches that the divide between cosmology and condensed matter is illusory. Both are expressions of how quantum fields, whether of helium atoms or empty space, organize themselves into coherent living matter. 55. Analog black holes in fluids produce horizon radiation like Hawking's picture. Physicists realized that certain fluid flows could mimic the causal structure of a black hole, a region where disturbances cannot escape. In such acoustic black holes, sound waves are trapped when the flow speed exceeds the speed of sound, forming a horizon. The equations governing these flows closely match those describing spacetime near real gravitational horizons, allowing the study of Hawking radiation in controlled laboratory conditions. Experiments with Bose-Einstein condensates, flowing water channels, and optical fibers have detected correlated pairs of phonons or photons emerging from these artificial horizons. The statistical properties of these emissions match theoretical predictions, giving tangible support to Hawking's claim that horizons radiate because of quantum fluctuations in the vacuum. These analog systems are remarkable not because they simulate the astrophysical scale, but because they reveal that the underlying mathematics of creation from the vacuum is universal. Wherever boundaries restrict waves, in fluids or spacetime, vacuum fluctuations adapt, generating real quanta. By reproducing cosmic events on a tabletop, physicists transform abstract predictions into measurable facts. The message is profound, the laws of the universe are scalable, and the vacuum behaves consistently whether under a star's gravity or a scientist's laser. 56. The dynamical Casimir effect appears in superconducting waveguides with fast boundary tuning. When the boundaries confining a field are moved or changed rapidly, the vacuum inside them cannot adjust instantly. Energy from the motion converts into real photons, a dynamical Casimir effect. Using superconducting circuits, researchers can emulate moving mirrors by modulating the effective length of a microwave cavity at gigahertz rates. The cavity emits correlated photon pairs that match the spectrum predicted for this effect. These photons emerge from vacuum fluctuations, not from thermal or electrical noise. They carry entanglement signatures confirming their quantum origin, forming a source of non-classical light usable in communication and computation. By controlling modulation speed and amplitude, scientists can tune the strength and frequency of emission, effectively pumping the vacuum like an engine. What's striking is the resemblance between this laboratory phenomenon and cosmological particle creation. The expansion of the early universe is mathematically equivalent to moving boundaries in time, both amplify vacuum modes. Thus, each superconducting cavity becomes a small echo of the Big Bang. The dynamical Casimir effect proves that motion and geometry alone can awaken the vacuum. Space need not be heated, charged, or illuminated, only changed quickly enough to reveal its latent energy. 57. Josephson junction noise measurements probe zero-point currents. Josephson junctions, thin insulating barriers between superconductors, support currents that flow without resistance governed by quantum phase differences. Even in total darkness and at millikelvin temperatures, small voltage fluctuations appear across these junctions. Part of this noise originates from zero-point motion of the electromagnetic modes inside the circuit, giving experimenters a way to measure vacuum fluctuations directly in the electrical domain. By analyzing spectral densities and comparing them with theoretical predictions, physicists separate thermal noise from quantum noise. The agreement between data and quantum electrodynamic theory is extraordinary, confirming that even at near absolute zero, circuits hum faintly with the vacuum's rhythm. This kind of precision metrology turns superconducting electronics into laboratories for fundamental physics. Josephson junctions not only underpin qubits in quantum computers, but also serve as windows into the ground state of the electromagnetic field. In essence, every quantum computer quietly listens to the vacuum as it operates. Its qubits and junctions interact with the ever-present zero-point current, proving that even the most advanced technology runs on the subtle energy of nothingness. 58. Quantum state tomography reconstructs the vacuum's squeezed quadratures. Quantum state tomography allows scientists to map the statistical distribution of a field's amplitude and phase, its quadratures. When applied to squeezed vacuum states, this technique reveals how uncertainty has been redistributed. One quadrature narrower, the other broader, yet their product constant. The resulting Wigner function, a quasi-probability landscape, often shows negative regions indicating genuine non-classical behavior. By performing tomography on microwaves, optics, and even mechanical vibrations, researchers can visualize the invisible. They see the fingerprint of the vacuum shaped by human control. The images look like soft ellipses in phase space, oriented according to the squeezing angle, portraits of manipulated silence. This visualization provides more than beauty. It lets scientists verify entanglement, calibrate quantum sensors, and validate noise reduction below the standard quantum limit. The vacuum ceases to be theoretical and becomes an observable object with measurable contours. Quantum tomography shows that the ground state is not empty but structured, a cloud of probabilities we can image, rotate, and quantify. It is like photographing the breadth of the universe, intangible yet real enough to measure pixel by pixel. 59. Wigner functions of non-classical states display negative values. In classical probability, values cannot go below zero. Yet when the Wigner function, a quantum analog of probability, dips negative, it reveals that a system occupies regions forbidden by classical physics. Squeezed states, Fock states, and superpositions like Schrödinger's cat. All show these negative values, and so does the engineered vacuum in high-precision experiments. These negative regions are not mere curiosities. They are the mathematical proof of quantumness. They indicate interference between mutually exclusive possibilities, the heartbeat of the quantum realm. Measuring them requires meticulous reconstruction of field amplitudes, often involving thousands of repeated measurements and advanced statistical inversion algorithms. In visual terms, a Wigner function looks like a smooth landscape of peaks and troughs, where the negative valleys glow as markers of coherence. Each valley says, here, the impossible is happening, and the vacuum allows it. By mapping these valleys, physicists see how energy and information dance within the ground state. The vacuum reveals its complexity, not random chaos but ordered strangeness, a quiet pattern of negativity underlying all creation. 60. Optical parametric oscillators create correlated photon pairs from vacuum seeds. Inside an optical parametric oscillator, A pump photon entering a nonlinear crystal can split into two lower energy photons, signal and Adler, whose energies add up to the original. What triggers this process is not an external spark, but the vacuum itself. Zero-point fluctuations provide the seed that allows the first pair to emerge. Once generated, amplification cascades into a beam of correlated photons. The outcome is a light field teeming with quantum correlations, pairs so synchronized that measuring one instantly reveals properties of the other. These sources form the backbone of modern quantum optics, enabling experiments on entanglement, teleportation, and quantum communication. The fact that such phenomena begin from vacuum fluctuations demonstrates how creation requires no external hand. The vacuum offers the initial fluctuation, and nonlinear interaction provides the amplification. Together, they turn nothing into something measurable and bright. Every pulse of squeezed or entangled light from an optical parametric oscillator is a controlled eruption of the vacuum's potential. It is the laboratory echo of the same process that might once have birthed the cosmos itself. Fluctuation amplified into form, silence transformed into light. 61. Spontaneous parametric downconversion begins from vacuum fluctuations. In quantum optics laboratories, a process known as spontaneous parametric downconversion has become one of the most reliable ways to generate entangled photons. A powerful laser beam enters a nonlinear crystal, and occasionally one of its photons splits into two with lower energy, called signal and Adler photons, whose properties are perfectly correlated. No external trigger initiates this splitting. The vacuum itself supplies the initial fluctuation that makes the process possible. Mathematically, the nonlinear crystal couples the strong pump field to the zero-point modes of the electromagnetic vacuum. These vacuum modes act as seeds that get amplified into real correlated photon pairs. If the vacuum were truly empty, the process would never begin. In this sense, every photon pair produced in laboratories around the world carries a signature of the vacuum's omnipresent fluctuations. The applications are vast. Quantum cryptography, teleportation experiments, and precision metrology all depend on the pairs born from this spontaneous process. The randomness of their generation is not chaotic, but quantum pure, offering the most secure randomness available in nature. Spontaneous downconversion embodies the paradox at the heart of physics. Nothingness, when tapped correctly, becomes a wellspring of order. Every entangled photon that emerges from these crystals is a visible reminder that emptiness is fertile ground, always ready to produce connection from silence. 62. Vacuum-seeded superradiance can burst from clouds of cold atoms. When a dense ensemble of excited atoms shares a common electromagnetic field, they can emit light collectively, producing bursts of radiation much more intense than the sum of their individual emissions. This phenomenon, known as superradiance, often begins spontaneously, seeded by the quantum fluctuations of the vacuum that synchronize the atomic dipoles. Even without a driving field, the atoms find coherence in the hum of emptiness. In laboratory conditions with ultra-cold atoms or Bose-Einstein condensates, researchers can observe how vacuum noise triggers these collective flashes. The timing and intensity of each burst depend on statistical fluctuations rather than deterministic control, yet the results are reproducible in ensemble averages, revealing an underlying law beneath apparent randomness. This interplay between coherence and chaos is striking. The vacuum provides the microscopic irregularities that allow macroscopic order to form. The light that bursts forth is not random. It is the orchestrated consequence of countless atoms resonating to the same invisible beat. Superradiance shows that emptiness is not mute, but a conductor of symphonies. That coherence, one of the most precious forms of order in physics, can emerge not in spite of the vacuum, but because of it. 63. Bose-Einstein condensates reveal zero-point sound at nanokelvin temperatures. When atoms are cooled to billionths of a degree above absolute zero, they collapse into a single quantum state, forming a Bose-Einstein condensate, a fluid that behaves like one giant atom. In this near-perfect stillness, where all thermal motion is frozen out, researchers still detect faint ripples of sound, zero-point excitations of the condensate's collective wave function. Even in absolute quiet, the system vibrates with quantum breath. These zero-point phonons provide a direct analogy to vacuum fluctuations in fields. They define the ground state of the condensate and determine its stiffness, pressure, and response to perturbations. By manipulating the trap potential or stirring the condensate gently, scientists can study how these fluctuations evolve, sometimes creating analogues of cosmological phenomena like expanding universes or Hawking-like radiation. The data are stunningly precise. Phonon spectra at nanokelvin temperatures follow quantum predictions perfectly, confirming that even in the absence of heat, fluctuations persist. The Bose-Einstein condensate becomes a tangible metaphor for the universe, calm on the surface, seething microscopically. In this condensed, whispering matter, we glimpse how the vacuum itself might behave as an ever-present substrate of potential, restless even in perfect cold, waiting for energy to awaken it into form. 64. Optomechanical strong coupling swaps energy between light and motion near the vacuum limit. In optomechanics, mirrors or membranes suspended in optical cavities interact with light so sensitively that a single photon can influence their motion. When the interaction strength surpasses losses, the two systems, optical and mechanical, enter the strong coupling regime. Energy quanta can oscillate back and forth between them, forming hybrid states where photons and phonons become indistinguishable. At this threshold, the mechanical element approaches its zero-point motion amplitude, and each quantum of vibration corresponds to a detectable shift in the light field. Experiments in this regime probe the frontier where classical motion merges with vacuum fluctuations. The mirror is no longer just a reflector. It becomes part of the quantum vacuum's machinery, trading energy with light itself. Such systems are candidates for quantum memories, converters between microwave and optical domains, and ultra-sensitive detectors. But they also play a deeper role. They make the vacuum tangible by letting macroscopic objects participate in its fluctuations. When a mechanical oscillator the size of a human hair hums in step with vacuum light fields, it collapses the distance between our world and the quantum realm. The vacuum ceases to be an abstraction. It becomes something we can touch, balance, and even listen to. 65. Feedback cooling plus squeezed light beats standard quantum limits. In measurement science, there exists a trade-off between precision and disturbance. Measure something too well, and the act of observation adds noise. But by feeding measurement results back into a system in real time, and by replacing ordinary vacuum with squeezed light, scientists can surpass this so-called standard quantum limit. The squeezed vacuum reduces uncertainty in one quadrature, while feedback actively cancels the back-action noise that would normally arise. This combination allows detectors to sense forces or displacements smaller than those dictated by classical quantum constraints. Gravitational wave observatories, nanomechanical sensors, and atomic clocks all stand to benefit. In each case, the improvement arises from engineering the vacuum rather than the material device. The idea marks a shift in how precision is pursued. Instead of trying to overpower noise, researchers redesign the noise itself, shaping the vacuum's fluctuations like sculptors working with invisible clay. It's a triumph of cooperation with nature rather than confrontation. This delicate control proves that progress in physics no longer means conquering the unknown, but partnering with it, learning the vacuum's rhythm, and using its own quantum music to hear the universe more clearly. 66. Quantum non-demolition tricks measure one observable while hiding from back action. In most quantum systems, measuring one property inevitably disturbs its conjugate partner. Position disturbs momentum, phase disturbs amplitude. Quantum non-demolition (QND) measurements sidestep this dilemma by focusing only on variables that commute with the system's Hamiltonian, ensuring that a measurement noise does not feed back destructively. In practice, this often involves cleverly timed interactions with light or auxiliary systems that record information without perturbation. In gravitational wave detectors, QND schemes monitor optical power or quadratures that reveal the signal, but remain immune to the photon shot noise that would otherwise shake mirrors. In atomic clocks, they allow repeated interrogation of ensembles without collapsing the collective spin state. These methods turn the measurement from a destructive act into a dialogue. The system whispers information to the detector while staying undisturbed, like a quantum echo that reveals its truth without breaking its silence. The ability to perform QND measurements shows that we are learning to listen to the vacuum respectfully, extracting knowledge without adding chaos, peering into quantum motion without silencing it. 67 Zeno effects show how repeated observation reshapes vacuum-driven dynamics. The quantum Zeno effect reveals that frequent measurement can freeze a system's evolution. By continuously observing a particle's state, one effectively resets its wave function repeatedly, preventing transitions that would otherwise occur due to vacuum fluctuations. Paradoxically, watching something too closely can keep it from changing, as though attention itself exerts physical control over possibility. This effect has been demonstrated in trapped ions, superconducting qubits, and donned atomic ensembles where transition probabilities collapse under continuous monitoring. The inverse Zeno effect, conversely, shows that under different conditions, observation can accelerate transitions instead. Both phenomena expose the intimate relationship between measurement, time, and the vacuum background driving spontaneous evolution. At a philosophical level, the Zeno effect blurs the line between observation and existence. It implies that the vacuum's random fluctuations are not independent of the act of measurement. Observation modifies the probabilities of their outcomes. It's a reminder that in quantum reality, even silence changes when you listen to it. The vacuum's murmur becomes a duet with the observer, each shaping the rhythm of the other. 68 Cavity quantum electrodynamics tracks single atoms crossing single vacuum modes. In cavity quantum electrodynamics (QED), atoms pass through high-finesse resonators that confine light between mirrors so perfect that photons bounce thousands of times before escaping. Inside, the electromagnetic field is reduced to discrete modes, each representing a standing wave of vacuum fluctuations. When a single atom interacts with a single mode, the exchange of energy becomes quantized and reversible, a microscopic handshake between matter and emptiness. Such experiments have observed vacuum-Rabi oscillations where an atom and cavity mode swap excitation back and forth coherently. The rate of these oscillations measures the coupling strength and reveals how geometry and field structure determine quantum behavior. This work forms the foundation of quantum networks and quantum computers, where information is encoded in these delicate atom-photon exchanges. But beyond technology, it demonstrates how controllable the vacuum has become. We can now position single atoms to feel the rhythm of a single vacuum mode and watch them dance accordingly. Cavity QED reduces the vast abstract concept of the quantum field to a tangible experiment. One atom, one photon, one tiny pocket of vacuum vibrating quietly yet infinitely. 69. Vacuum Rabi splitting demonstrates coherent exchange with the ground state field. When an atom couples strongly to a resonant cavity mode, its energy levels split into two new hybrid states, the hallmark of vacuum Rabi splitting. This splitting occurs even when no real photons populate the cavity, showing that the atom interacts with the vacuum field itself. The vacuum acts as a partner in the atom's quantum dance, creating energy shifts purely from virtual exchanges. By scanning the frequency of atomic transitions, scientists observe the double-peaked signature of this phenomenon, confirming that coherence arises not from light, but from the structured emptiness between mirrors. Each peak represents a shared excitation between the atom and the vacuum, one part matter, one part field. This realization bridges the microscopic and the metaphysical. It proves that the vacuum is not an idle spectator. It is part of the system, shaping the energy landscape even in apparent stillness. Vacuum Rabi splitting turns nothing into something measurable. The void inside the cavity acquires structure, tone and resonance, as if emptiness itself learned how to sing. 70. Spontaneous emission can be inhibited by photonic bandgaps that edit vacuum modes. In ordinary space, an excited atom will eventually emit a photon and decay. But if that atom is placed inside a photonic crystal or cavity where its transition frequency lies inside a bandgap, a range of forbidden light modes, emission can stop entirely. The atom finds no vacuum mode available to accept its photon. The result is an artificial stillness. Spontaneous emission frozen by design. This discovery showed that decay is not an inherent property of matter, but a consequence of the environment's vacuum structure. By changing that structure, one changes time itself at the atomic level, stretching lifetimes from nanoseconds to seconds or more. Technologically, this control enables efficient lasers, stable qubits, and devices that manipulate light-matter interaction at will. Conceptually, it reveals that the boundary between something and nothing is negotiable. When scientists silence an atom's decay by editing the vacuum around it, they prove that time's flow for matter depends on the music played by the field of emptiness, and that by rewriting that score, we can pause the rhythm of decay itself. 71. Super-radiant phase transitions test how matter organizes with the vacuum field. When a large collection of atoms couples to a single electromagnetic mode, the system can undergo a phase transition where the vacuum field itself becomes macroscopically occupied. This super-radiant phase transition represents a state of collective coherence, where matter and the vacuum field merge into a single entity that oscillates in harmony. Instead of atoms emitting light individually, the entire ensemble and the field behave as one body, sharing a unified wave function. Such transitions have been realized in ultra-cold atom systems and superconducting circuits, where the coupling between particles and photons is strong enough to reorganize both. The boundary between emitter and field vanishes, atoms polarize the vacuum, and the vacuum feeds back, stabilizing the new order. The ground state changes qualitatively, proving that emptiness can become structured when pushed beyond a critical threshold. In this regime, photons exist not as individual quanta, but as collective excitations of a hybrid light-matter fluid. Experiments observing this phenomenon hint at deep analogies between condensed matter physics and quantum field theory, suggesting that what we call empty space could similarly undergo symmetry-breaking transitions on cosmological scales. The super-radiant phase transition stands as a metaphor for the universe itself. When enough energy is confined within a single field, the vacuum awakens, coherence emerges, and light becomes indistinguishable from the matter that emits it. 72. Rydberg atoms magnify tiny vacuum shifts through enormous orbits. Rydberg atoms, atoms with one electron promoted to a very high energy level, possess orbits thousands of times larger than normal. Their exaggerated size makes them exquisitely sensitive to electric fields, magnetic disturbances, and vacuum fluctuations. Even the faintest shift in the surrounding zero-point field can nudge their energy levels detectably, turning them into magnifying glasses for the subtle structure of the vacuum. In laboratory conditions, these giant atoms serve as probes for Casimir-Polder forces near surfaces, measuring how the vacuum's electromagnetic modes alter as boundaries approach. Because their electrons roam far from the nucleus, Rydberg atoms effectively sample large regions of space, averaging over local variations in the vacuum energy landscape. Such measurements refine our understanding of how atomic properties emerge from field interactions. They also test predictions about retardation effects and dynamic polarizabilities, corrections that stem entirely from the restless vacuum. By inflating atomic size to near macroscopic scales, Rydberg physics makes the invisible visible. Each spectral shift is a whisper from the vacuum, magnified until even our instruments can hear the hum of space itself. 73. Atom interferometers feel phase shifts from vacuum electromagnetic fields near surfaces. Atom interferometry exploits the wave nature of matter. Atoms split, travel along separate paths, and then recombine, forming interference fringes sensitive to tiny phase shifts. When one arm of the interferometer passes close to a surface, vacuum fluctuations near that surface modify the atomic energy levels slightly, introducing a measurable delay relative to the other path. This effect provides one of the cleanest measurements of Casimir-Polder interactions at micrometer distances. The atoms are free-falling test particles responding only to the vacuum's invisible pull. Comparing observed phase shifts with theoretical models allows scientists to refine the parameters of quantum electrodynamics and even test hypothetical short-range forces predicted by new physics. Atom interferometry translates the abstract energy of the vacuum into tangible patterns of light and dark on a detector, a visible interference of nothingness itself. The experiment shows how emptiness leaves fingerprints even on particles moving through silence. Every fringe observed in these instruments is a message from the quantum vacuum encoded in phase and rhythm, a direct conversation between matter and the void. 74. Quantum reflection bounces slow atoms from attractive Casimir tails. Under classical physics, a particle approaching an attractive potential would always fall in, but quantum mechanics allows reflection even from attraction if the particle moves slowly enough, a phenomenon called quantum reflection. For atoms near surfaces, the Casimir-Polder potential provides exactly such a slowly varying attraction, and experiments have shown that ultra-cold atoms can reflect from it without touching the surface at all. This mirror made of pure vacuum force is astonishing. Atoms bounce off the gradient of emptiness, not a solid barrier. The reflection probability depends on the shape of the potential, which in turn depends on the local vacuum field structure. Measuring reflection rates lets physicists map how the vacuum's influence changes with distance and material composition. Quantum reflection blurs the line between contact and non-contact, matter and nothing. It reveals that even an attractive void can repel when approached delicately enough. This is perhaps the purest image of the quantum world, a single atom, drifting in silence, bouncing off the invisible hand of the vacuum as though space itself had texture. 75. Ultra-cold neutrons sense quantum states in Earth's gravity with vacuum boundary effects. Even gravity can reveal quantum discreteness. When ultra-cold neutrons are allowed to bounce on a horizontal mirror in Earth's gravitational field, they occupy discrete vertical energy levels, standing waves of matter above the surface. The gap between mirror and neutron defines a boundary that modifies vacuum fields, adding subtle corrections to these gravitational quantum states. Measurements of transition frequencies between these levels have achieved extraordinary precision, sensitive enough to probe hypothetical forces or spatial variations in the vacuum. The interplay between gravity, quantum confinement, and vacuum effects forms a unique window into how the smallest and largest laws of physics merge. Each neutron, silently oscillating above the mirror, traces out a waveform sculpted by two invisible architects, gravity pulling downward and the vacuum pressing upward. The resulting pattern is a balance between curvature of space-time and fluctuation of fields. Through these experiments, physicists confirm that even near Earth, amid air and light, the quantum vacuum participates in shaping motion. Space is never neutral. It sculpts everything that moves within it, from cosmic galaxies to solitary neutrons hovering above a mirror. 76. Gravitational wave detectors now operate with injected squeezed vacuum light. Modern observatories like LIGO and Virgo measure changes in mirror separations smaller than a proton's diameter. At that sensitivity, quantum noise in light becomes the limiting factor. To overcome it, scientists inject squeezed vacuum states into the interferometer's unused port. By reducing uncertainty in the measured quadrature, they cut quantum noise, making the detectors quieter than the natural vacuum itself. This technique has already extended the observatory's reach by billions of light years, letting them catch whispers of black hole collisions that would otherwise be lost. The improvement doesn't come from stronger lasers or heavier mirrors, but from refined emptiness. Reshaped vacuum fluctuations guiding how light behaves at the edge of detectability. The squeezed vacuum entering those giant tunnels of light is a triumph of human subtlety. It demonstrates that progress in cosmology now depends as much on mastering nothingness as on harnessing energy. Each gravitational wave detected carries two stories, one from merging black holes across the cosmos, and one from the quantum vacuum on Earth that allowed us to hear them. 77. The standard quantum limit fell in practice once squeezed vacuum entered the interferometer. For decades, the standard quantum limit was seen as an immutable barrier, the balance point between shot noise and radiation pressure noise in precision measurements, but by manipulating the vacuum, scientists have surpassed it. Squeezed states of light introduced into interferometers reshape uncertainty, concentrating it in unmeasured variables and freeing the signal from its constraints. The first successful demonstration showed measurable improvements in signal-to-noise ratio without violating any fundamental laws, only rewriting the assumptions of what noise meant. The vacuum structure, once fixed, became pliable. This achievement is more than technological, it is philosophical. It reveals that even the supposedly random flaw of the universe can be engineered. The vacuum is not destiny, it is material for design. By surpassing the standard quantum limit, humanity confirmed that our deepest limitation was never nature itself, but our lack of understanding of how silence works. 78. Shot noise reduction reveals how vacuum fluctuations set measurement flaws. In photon counting systems, shot noise arises from the discrete nature of light and the random arrival times of photons. At its core, this randomness stems from vacuum fluctuations that define how photons emerge from fields. Even in the best laser beams, the underlying noise pattern reflects the vacuum's own uncertainty. By injecting squeezed vacuum or employing correlation-based detection, scientists can lower this noise, achieving clarity once thought impossible. Each decibel of improvement represents not a suppression of photons, but a reorganization of the vacuum's statistical fabric. Recognizing shot noise as a manifestation of vacuum behavior reframes measurement limits. It means that the boundary of precision is not hardware or environment, but the structure of emptiness itself. When laboratories around the world push past that boundary, They are not silencing chaos. They are tuning the song of the vacuum to a more harmonious frequency, using its rhythm to reveal the universe's faintest signals. 79. Radiation pressure. Noise is the moving mirror side of the same vacuum coin. Just as photon number fluctuations produce shot noise, fluctuations in photon momentum cause radiation pressure noise. Mirrors in interferometers jitter under the push and pull of light quanta, even when the beam's power is constant. These random kicks arise from the zero-point fluctuations of the electromagnetic field, directly linking macroscopic motion to microscopic vacuum behavior. In delicate experiments, this noise appears as a low-frequency rumble that sets a fundamental sensitivity limit. Reducing it requires heavier mirrors, quantum correlations between light and mechanics, or clever measurement strategies that cancel the kick statistically. Each approach acknowledges the same truth: the vacuum shakes the world, however gently. At this scale, quantum backaction becomes tangible. The mirrors respond to the same vacuum that defines their position uncertainty, binding cause and effect in a perfect circle. Radiation pressure noise is not an obstacle but a reminder, a quiet handshake between the weight of matter and the weightlessness of the vacuum field pressing against it from all directions. 80. The zero-point field shapes thermodynamic limits on amplifiers and sensors. Every amplifier adds noise, and every sensor faces a fundamental limit on sensitivity. That limit is not due to engineering flaws, but to the presence of the zero-point field. Any attempt to extract information from a signal necessarily interacts with the vacuum fluctuations embedded in that channel. Quantum-limited amplifiers reach this boundary, achieving the best possible performance consistent with the laws of physics. In microwave and optical systems, these limits manifest as minimum added noise equal to half a quantum per mode, the contribution of the vacuum itself. Engineers design parametric amplifiers, Josephson devices, and quantum-limited detectors to approach this frontier, balancing gain and added uncertainty as delicately as possible. These constraints connect thermodynamics and quantum mechanics. They show that measurement, amplification, and even temperature are expressions of how information and the vacuum intertwine. When a sensor reaches the quantum limit, it doesn't mean perfection has been achieved. It means the device has finally met its equal, the silent, ever-present hum of the vacuum, which refuses to yield but gladly allows us to touch its edge. 81. Passive materials cannot yield network from vacuum energy without external drive. The idea of harvesting infinite energy from zero-point fluctuations has long lured dreamers and frauds alike. But physics draws a firm boundary. The vacuum's energy is uniform and cannot be tapped to produce network. Any attempt to extract it from one region must pay an equal price elsewhere, as guaranteed by the conservation laws and the second law of thermodynamics. Casimir forces, for example, can move plates but not generate perpetual motion. Once separated, the energy required to restore the setup matches what was gained. The vacuum provides no gradient, no reservoir that can be drained, only equilibrium. Still, this doesn't diminish its grandeur. The vacuum's energy sets all motion, defines all interactions, and stabilizes the cosmos. Its uniformity is what prevents chaos, not what hides treasure. The dream of free energy misunderstands the miracle before us. The notion of fluctuations can exist everywhere and yet sum to stillness. The vacuum gives us balance, not profit, harmony, not fuel. 82. No extraction schemes have bypassed the second law with zero-point energy. Over the decades, inventors have claimed devices that tap the zero-point field for limitless power, but none have survived scrutiny. Each proposal overlooks the fundamental symmetry of the vacuum. For every fluctuation extracted, another of equal energy appears elsewhere, preserving equilibrium. Even quantum rectifiers, diodes, or asymmetric geometries fail because the vacuum has no preferred direction. Quantum electrodynamics is mercilessly consistent. The same mathematics that predicts Casimir forces and Lamb shifts also forbids perpetual motion. The vacuum can lend energy locally but demands it back instantly, its generosity perfectly balanced by its accounting. Yet the persistence of such dreams speaks to something poetic, a longing to interact directly with the universe's foundational energy. We cannot harvest it, but we can hear it, measure it, and even shape it. That alone is remarkable. The vacuum remains untouchable as an energy source, but invaluable as an inspiration. the unreachable harmony that still powers our curiosity. 83. Reputable experiments reserve the phrase free energy for efficiency upgrades, not miracles. In serious research, free energy no longer means limitless power from nothing. It refers to usable energy extracted from systems that are already out of equilibrium. Chemical gradients, temperature differences, or quantum correlations temporarily available before balance returns. In quantum optics, for instance, squeezing the vacuum redistributes fluctuations, providing apparent gains in precision without violating any law. By redefining free, scientists emphasize efficiency and control rather than fantasy. The vacuum's role becomes that of mediator, setting boundaries and offering windows of advantage where clever design can momentarily tilt the scales. This discipline has shifted the conversation from wishful thinking to practical mastery. The focus is no longer on breaking nature's laws, but on dancing with them, using their subtleties instead of opposing them. True freedom lies not in stealing energy from nothing, but in understanding how nothing sustains everything, and using that understanding to build within the universe's rules, not against them. 84. Creative propulsion ideas study how to modulate fields without breaking conservation laws. Even though extracting network from the vacuum is impossible, some engineers explore whether dynamic modulation of electromagnetic fields could produce momentum exchange with the vacuum itself, a kind of reactionless propulsion. Theoretically, such schemes would require interactions that exploit field asymmetries without violating conservation laws. None have yet produced measurable thrust, but the investigations sharpen our grasp of how vacuum fields couple to matter. At their best, these studies lead to improved resonant cavities, plasma drives, or metamaterial propulsion concepts that obey known physics but push it to its edges. At their worst, they drift into pseudoscience. The difference lies in discipline, a rigorous respect for the symmetry and balance of the zero-point field. Even failed attempts add value by confirming nature's consistency. Each null result reinforces that the vacuum, though flexible, is fair. It yields only to truth, not to wishful engineering. In the end, the greatest propulsion the vacuum gives us is intellectual. It drives imagination, forcing human creativity to accelerate toward a deeper understanding, instead of impossible machines. 85. The quiet power of the vacuum remains a background actor that sets what is possible. Every experiment, every atom, every beam of light performs upon the stage of the quantum vacuum. It is the baseline of existence, the zero from which all energy and form emerge, and it neither rests nor rages. It simply persists, enforcing the symmetries that hold the universe together. The vacuum is not empty. It is full of laws, balance, and quiet potential. Without it, there would be no inertia, no forces, no structure, no time. The vacuum defines what can exist and what cannot, whispering its constraints into every equation and experiment. The silence we perceive between stars is not nothingness, but a vast ocean of subtle motion, too fine for our senses, yet essential for everything we are. Humanity has learned to listen to that silence, to measure it, to shape it, even to momentarily rewrite it. Each success in quantum optics, cosmology, or gravitation is a deeper conversation with this invisible foundation, and in that conversation, one truth endures. The universe does not rest upon emptiness. It is emptiness, vibrating with infinite patience, sustaining all creation through the silent power of zero-point energy. 86. The vacuum links time's flow to quantum uncertainty. In quantum theory, the passage of time is inseparable from the fluctuations that animate the vacuum. Every process, from particle decay to cosmic expansion, unfolds against this restless background. The zero-point field provides the reference for energy, and because energy and time are conjugate variables, uncertainty in one implies fluidity in the other. In this way, the vacuum is not only the origin of space, but also the quiet engine of temporal rhythm. Without fluctuations, clocks would never tick and transitions would never occur. The apparent stillness of empty space is, paradoxically, what makes motion and change possible. In the equations of quantum mechanics, time emerges as the bookkeeping of the vacuum's internal motion, a measure of how probabilities breathe. Some modern theories even suggest that time's arrow arises from how quantum information disperses through the vacuum entangling everything that exists. As correlations spread, events acquire direction, and the now moves forward. Thus, the vacuum does more than fill the universe. It unfolds it. Time itself may be the slow unfolding of zero-point energy across dimensions, the eternal heartbeat beneath every moment of existence. 87. Life itself may rely on the quiet background of vacuum stability. Biology rarely acknowledges the vacuum, yet every biochemical reaction, every photon striking the retina, every electron passing through a cell membrane occurs within it. The constants of nature, either fine structure constant, electron mass, speed of light, are all tuned by the vacuum's properties. Were the vacuum slightly different, chemistry would fail, molecules would not bind, and stars could not forge the elements that make life possible. This perfect tuning arises not from design, but from balance. The vacuum's energy density, its permittivity and permeability, and its stability across cosmic time ensure that matter and radiation remain in harmony. The same quantum fields that make virtual pairs flicker into existence also define how enzymes fold, how DNA absorbs ultraviolet light, and how oxygen binds to hemoglobin. In this sense, life is not separate from the vacuum. It is the vacuum's most complex vibration. Cells and consciousness are intricate modulations of the same zero-point field that fills interstellar space. Recognizing this connection elevates existence from accident to resonance. Every breath is the vacuum breathing through us, order, awareness, and meaning, born from the infinite stillness that underlies everything alive. When we close our eyes tonight, the quiet we sink into is not truly empty. Every breath, every heartbeat, every flicker of thought still floats within a sea of invisible motion, the zero-point field humming beneath all things. What we call nothing is the most active presence in existence, the silent current that carries galaxies, particles, and dromedarums alike. As you fall asleep, imagine yourself suspended in that vast stillness, the same stillness that holds the stars in balance. You are not separate from it. You are part of its rhythm, a momentary wave on the endless ocean of the vacuum's calm power. Sleep inside that truth, and let the silence remind you that even emptiness is alive. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.